Welcome back. So today we're going to be talking about we're going to be doing some basic groundwork for topic 4, chemical bonding and structure. Um, so today I would like to focus on defining first what is an ionic and what is a covalent bond, and then I would like to just go over some brief naming rules. They're both very short topics, so um, I'm just going to group them together. Without further ado, let's start. So, a chemical bond is a electrostatic force that holds two atoms or ions together. Um, we there are two different extremes that we call ionic and covalent. However, the reality is that it's more of a continuum because what defines these terms is something that is, well, not necessarily discrete, but it's continuous. Anyways, but with that said, um, if the electronegativity difference is high, electrons are more or less transferred. They could theoretically be in the other atom, but they generally tend to stick to one atom and one atom only. So highly electronegative elements gain electrons, tend to gain electrons and form anions, therefore, and generally elements with low electronegativities tend to lose electrons and form cations. This loss and gain of electrons is such that both types end up with noble gas electron configurations, which is generally the goal of bonding. Generally, the goal of bonding is to achieve, well, noble gas electron configurations, which are extremely stable and extremely unreactive. So that's generally the name of the game. Um, if the electronegativity difference is high, it obviously means that electrons are transferred, and we call this an ionic bond. For all intents and purposes, define this. Um, we define the barrier as ionic and covalent at a difference of electronegativity at here it says 1.65, but the IB tends to use 1.8. If it's greater than 1.8, then it's considered ionic, which that's there's that. And metals generally tend to form ionic bonds with nonmetals because the electronegativity difference tends to uh, tends to the electronegativity difference tends to be much greater than 1.8, usually around 2, 2.5. The greatest one you can get is francium and fluorine, and that one I believe has a difference of 3.2. Yeah, 3.2. And and then if we go to the opposite end of the spectrum, if we have a low electronegativity difference, we call that a covalent bond, and this means that the electrons are shared between the two atoms evenly, and so a covalent bond is formally defined as the electrostatic attraction between a pair of shared electrons and the two nuclei sharing them. Uh, However, most people normally associate covalent bonding with the idea of sharing electrons, which is good enough. And if the electronegativity difference is less than 1.8, it's considered covalent. Um, and then even within covalent bonds, there's a distinction made between pure and polar covalent bonds. The pure covalent bonds tend to have electronegativity differences of less than 0.5, whereas polar covalent tends to be between zero point 0.5 and 1.8 difference in electronegativity. Um, Nonmetals generally form covalent bonds with other nonmetals because neither is electronegative enough to steal the electrons fully. However, they both need to gain to get that noble gas electron configuration. So, in essence, sharing is the only way they can do that. This I already talked about. Um, how while we do give categorizations to these things, the point is that generally, if we define chemical bonds as the difference in electronegativity, the strength and the difference in electronegativity, my point is that there's a continuum of bonds, um, and this is not a discrete thing. It's more of a categorization. So, if it falls, so what determines the strength of a chemical bond is the difference in electronegativity. The higher that is, the stronger it is. And generally, we tend to categorize. Okay, if it falls within this range, it's this. If it's within this range, it's this. If it's within this range, it's this. So, if it's low, With some of the diatomic elements, there is actually no electronegativity difference, and that is a true pure uh, covalent bond. However, something like the CH bond, which the difference in electronegativity between carbon and hydrogen is, I believe, zero point 0.4. We call it a pure covalent bond. However, in reality, there is some slight um, pulling of the electrons. There's some very, very slight uneven sharing bias towards carbon in that bond. However, we still call it pure. So my point is that it's a spectrum. It's not really a discrete thing. And if it falls within a certain range, then we just call it one or thing. My point is just to try and get you to appreciate that. Moving on. Now we can use this to determine molecular polarity, at least for very simple molecules. So a polar molecule is something that has ends of opposite charge. So the way you can accrue this is that the difference in electronegativity causes the electron distribution to be pulled towards one side of the molecule, and this would create a slight negative charge on that end of the molecule because the electrons are more toward it, and in essence it has more electrons than protons, even though that's really not how it works. But since the electron distribution is more biased toward that side, it essentially, as a result of that, it acquires a slight negative charge, and the other side would acquire a slight positive charge since there's a deficit of those electrons. And we call a polar molecule a dipole. Dipole moment is a property of something polar. It's essentially an arrow pointing to the positive and negative ends of the molecule, with the arrowhead pointing toward the negative side, and then you can clearly see this plus toward the positive side, this little plus thing here. Metals generally don't tend to form compounds with each other since they have low ionization energies, low electronegativities, and few valence electrons to begin with. They actually bond to something according to the electron C model, which we'll talk about a bit later. So, just to summarize the major concepts, uh, here we have the type of bond. Here we have the difference in electronegativity, the example, the unbounded atoms, the bonded atoms, and then here the type of bond. So here this is a pure covalent bond. This is a polar covalent bond. The difference is 0.9. And as you can see here, they share the electrons. However, since chlorine is more electronegative, this has a slight negative charge. Hydrogen has a slight positive charge. And then here we have an extreme example of an ionic bond, francium fluoride. Fluorine has a much, much, much greater electronegativity than francium, so therefore this is an anion, this is a cation, and the electrostatic forces of those ions hold each other together and form what is an ionic bond. Next, we're going to go on to naming these compounds. There's a bunch of simple naming rules for inorganic compounds, which this is what we're going to cover. So, predicting formulas for binary ionic compounds, you're expected to know the common ion charges. So, we covered that in the periodicity chapter. So, it's just a matter of adding cations and anions until the net charge is 0. So, for instance, here, predict the empirical formulas of those. Let's do a worked example here. Why don't we do C, Al, and Cl. So if we move over to our screen here, so Al tends to acquire a charge of 3 plus, and then we need Cl. Cl tends to form a minus ion. C, the net charge here is 2 plus, 1 plus, 0 plus, so the empirical formula is AlCl3. Right. I need to now erase this and go back to the main screen. Right. And then when we name them, it's for simple naming, we go cation, anion. So, and the way we name ions is just the element name. So, for example, Na1 plus is called the sodium ion. Ca2 plus is called the calcium ion, and then lithium is called the lithium ion. And then monoatomic anions have the prefix "ide" ion. to signify that they are an anion. Um, so you generally replace the last vowel sound with that prefix "ide." So, for example, sodium chloride or potassium iodide, um, for example, or let's see, magnesium fluoride. Yeah, magnesium fluoride. Yeah. So that's sort of how we go about naming things. Um, if a um, if a monoatomic ion has more than one possible charge, so mainly this would apply to transition metals, which can have multiple charges, which we discussed in a previous video. You generally specify what charge it has by using a Roman numeral, so iron 2 ion or iron 3 ion or silver 1 ion. Polyatomic cations are rare, and then now we're going to go to talk about. So those are for monoatomic ions. For polyatomic ions, again, we'll split them to cations and anions. There's only one real one you're expected to know for the cation side, and that's ammonium. Pretty easy. And then these polyatomic ions are very common. I would definitely memorize the ones that I'm about to highlight right now. Memorize those. Um, and then here's some other common inorganic ions that you're expected to know. Memorize the ones that are highlighted because they will come up later over and again in this course. And I really do recommend memorizing them, and there's no real way around it. They tend to be oxyanions, so anions containing oxygens, and they generally have names ending in ate or ite. Um, the ate ending is used for the parent oxyanion, and then if it has one less oxygen, we use the ite prefix. If it has one more, we use the per before. No, wait, is it a prefix or suffix? Fuck. We use the ate suffix ending. We use the ate ending for the parent oxyanion and the ite ending for the oxyanion with one less oxygen if it's applicable, so see below. And then we have the prefixes hypo and per to indicate more or less than. So to save you a little bit of trouble, if you can remember that ite is just one less oxygen than parent oxyanions, you go down from having to memorize this table to, effectively, if I can get this to work here, the ones that delete, you effectively, if you can remember what the prefixes and suffixes mean, you effectively have to go from memorizing that to just, hang on, just this column here, which I'm sure you can memorize. What is that, 5 things? That is probably much easier for you to just memorize than the other stuff. I'm trying to. Right. So that's pretty much easier, and then we can again do the same sort of thing. So for example, we can have sodium carbonate, and you could also add H plus to protonate these, and then we would call it hydrogen carbonate or whatever. Memorize these, just makes your life easier, and then that's really that simple. Lastly, for covalent compounds, we tend to use the the lower electronegativity element first, followed by the higher ones with the same prefixes of the monatomic anions. So, carbon dioxide, phosphorus tribromide, sulfur diiodide, and so on and so forth. We just the thing with the more electronegative element gets the anion prefix because it's pulling on the electrons more. And although it doesn't behave like an anion, it's used to denote where, I suppose, my best guess is the way you can remember that is just it's where the electrons would go had it been an ionic bond. Where are they biased towards? Some well-established non-systematic names continue to be used, so water, ammonia, hydrogen peroxide. If a compound is network and not molecular, its empirical formula is used for naming. And yeah, I think that's about it. So yeah, thank you for watching. And don't forget to like and subscribe.